Welcome back. So far so good for macroscopic electric field. So now the mystery of these mathematical difficulties have been to a large extent overcome by the modern theory of electronic polarization by Dr. Rest and David Vanderbilt. As I said, within perturbation theory, those difficulties have been solved already a few years before, giving us the possibility of calculating the electric response of insulators within a density matter that is already 20 or more years ago. So how about perturbations that are well behaved, that is not as pathological as the microscopic electric field, but still are not periodic. So, lattice periodic. Suppose that a monochromatic perturbation has a periodicity different from the unit cell, from the lattice periodicity. This is basically what happens when you have phonons of finite wavelengths, right? And you know that phonons can be classified by their momentum or quasi-momentum, their wave vector, and their potential, the potential associated to it, varies in space periodically with a wavelength to 2 pi over q that is larger than the lattice spacing of the system. Remember that the key ingredient of perturbation theory, this right-hand side of density functional perturbation theory equations, is the projection over the empty state manifold of the product of the perturbing potential times the unperturbed wave functions. The unperturbed wave functions obey the Bloch theorem. They are classified by a wave vector, they are defined by the wave vector k, that is a good quantum number. If you multiply a Bloch state of wave vector q by a potential that has a wave vector k times a potential that has wave vector q, the resulting product will have wave vector k plus q, because this would carry along a phase e to the I k r. This will carry a phase e to the I q r. The product will be a phase e to the I q plus k r. But then on the left hand side you have an operator that is lattice periodic, right? Because here you have the Hamiltonian, forget about this complication, here forget about this. You have basically an operator that is lattice periodic. So if you take the solution of this system will be the inverse of this operator, in quotation mark, because we saw that this inverse has some mathematical difficulties, but let me assume that we can invert this for the sake of the symmetry argument I'm going to give. We can assume that this can be inverted without difficulties. So phi prime is equal to the inverse of this lattice periodic perturbation acting on this right-hand side that has periodicity q plus k. But the inverse of a lattice periodic operator is a lattice periodic operator. So the inverse of this applied to this will carry the same wave number as the wave number of the function to which it is applied. We conclude that phi prime k plus q has the same wave number as the right-hand side. Not surprisingly, not quite surprisingly. If I apply a perturbation of wave vector q, then the perturbation to the wave function of vector k will have wave vector k plus q, the same wave vector as the perturbing potential. Because of this, you do some algebra for the calculation of the density. Because of this, in the density you have to multiply u star k times the perturbed wave function, which has wave vector k plus q. This u star k will have a wave vector minus k, because it will be e to the I kr complex conjugate, that is e to the minus I kr. This e to the minus I kr will drop the e to the plus I kr here. To cut the long story short, this product will have wave vector q, which is good news, because this says that the perturbed density has, well, the perturbing density, the first order correction to the density has the same wave vector as the perturbing potential. Very good news, because this allows us to close the self-consistent cycle without breaking the symmetry. I start with the potential which has a wave vector q. I obtain a density that has the same wave vector q. Then the self-consistent potential, that is the Hartree potential generated by a function of wave vector q, will have the same wave vector as well. Why? Because the linear operator that relate the density to the potential is lattice periodic. It is basically the Coulomb operator. It is 1 over r minus r prime. It is lattice periodic. So I take a density of wave vector q. I apply a lattice periodic operator to obtain the potential. The potential will be of the same wave vector, and hence the output potential of the self-consistent cycle will have the same wave vector as the input potential. Good news. This means that we can close the loop of self-consistency without breaking the symmetry. And notice that this equation here, if you write this equation in terms of the periodic part of these block states, the periodic part of these block states, by definition, is periodic. So it only carries information over the unit cell. Basically, the solution of this linear system, even though it describes a perturbation that may be as large as many unit cells, but the information that is hidden in these functions that we solve for with this linear system is only contained into a unit cell. So the mathematical and algorithmic complexity of this linear equation is the same as that for an unperturbed system. So basically, even though the supercell that would be needed to accommodate such a long wavelength perturbation could contain many atoms, even very many atoms. I mean, the number of atoms contained in this supercell is equal to the number of atoms in the unit cell times the ratio between the wavelength of the perturbation to the size of the system. The wavelength of the perturbation is arbitrary, and this number of atoms is arbitrary. So if I were to describe this with supercells, I would need the very large supercells. But in order to solve this linear equation, I only need elementary cells. So in order to calculate phonons for a system with 2 atoms per cell, say silicon, gallium arsenide, sodium chloride, you name it, you consistently, in the loop, in the self-consistent loop for the linear response equations, you consistently only and always work with 2 atoms per cell. You never have to consider all the many atoms that would be comprised in the supercell which accommodates the perturbation. Very, very important. This is what allows us to calculate complete phonon dispersions at arbitrary wavelength in extended systems. Here is the expression for the potential that I described in words before. Andrea, will you talk about the polar? No, so I have to go. I have to do this. Okay.
In this connection, this is true only if the perturbation is truly monochromatic. But in real experimental situation, there are always spread little bit, right?
Because of linearity, you treat each Fourier component independent of the other. Because of linearity. So the response to a sum of many monochromatic perturbations is equal to the sum of the responses in the linear regime. Okay? Effective charges. Someone was asking before effective charges before. Let us see what happens for lattice vibrations in polar materials. Suppose you have a polar material such as sodium chloride, and suppose that you have a zone center distortion where you move all the atoms periodically in the same way. I want to express, because the atoms carry a charge, then by moving them I may induce a macroscopic polarization in the system. This macroscopic polarization would produce a macroscopic electric field. Then the energy as a function of the nuclear displacement will depend on the nuclear displacement directly, because ions are held together by springs, in quotation marks, but also because of the displacement gives rise to an electric field. Then you have to take into account the electrostatic energy stored into the energy stored into the electrostatic field. So in general, I have to write the energy as a quadratic form of the distortion and the field. I will have the quadratic term for the distortion, which is simply u squared times the bare frequency, omega 0. Then I will have the energy stored into the field, that is quadratic into the field itself. And then, in general, I will have a coupling between the two. And the coupling between the two is, by definition, the effective charge Z. So the effective charge Z is the second derivative of the energy with respect to the displacement and to the field. Right? Let us calculate the forces acting on the atoms and the electric induction corresponding to a given field. The force is given by the derivative of the energy with respect to the distortion, and it will have a mechanical component that is just the harmonic restoring force, plus an electric component because the atoms, the ions, are charged, so they respond to the field that they generate by themselves. Analogously, the electric induction is the derivative of the energy with respect to the field that is given by this expression. Now, if you have a transverse excitation, this means that the wave vector is perpendicular to the displacement, and in high symmetry the displacement is parallel to the field, so the wave vector is perpendicular to the field. This means that the rotor of the electric field, that is the cross, the vector product between Q and E in reciprocal space, has to be 0. So the the displacement is perpendicular to the wave vector, and in order for this equation to be fulfilled, you have to have a zero electric field for transverse excitations. For longitudinal excitations, it is not. If you do a little bit of simple algebra, you will see that it is not the electric field that has to vanish, but it is the electric induction that has to vanish. So in one case, it is this object that vanishes, and so the forces for transverse excitations, the electric field is zero, and the force is given only by its mechanical component, whereas for longitudinal excitations, you have that it is not the field that is zero, it is the induction that is zero, and so you have that the field is equal to minus u, and you combine this, and you see that the restoring force, instead of being given only by the mechanical component, is given by the mechanical component plus a correction that is proportional to the effective charge. We conclude that for polar materials, lattice vibrations in the long wavelength limit near the zone center tend to two distinct limits, to two distinct frequencies, according to whether the polarization of the vibration is perpendicular, transverse, or parallel longitudinal to the wave vector. Last effort, just the next 2-3 minutes, 5 minutes. In elementary textbooks on quantum, on solid state physics, phonons are described in terms of interatomic force constants. Right? These interatomic force constants are nothing but the Hessian of the energy with respect to the displacements we started from a few slides ago. This expression here. These interatomic force constants are short-ranged as far as the mechanical components are, the mechanical contribution is concerned, but it also has a long-range contribution due to the fact that because of the argument I tried to explain before, when you move an ion at some position, this movement would induce a dipole moment on that ion. So the dipole moment induced by a distortion at some point will introduce a dipole moment, a long-range interaction with dipole moments induced to other positions. When you do the Fourier transform of this, the Fourier transform of the interatomic force constants is basically the dynamical matrix whose eigenvalues give the phonon frequencies. And because of this long-range character of the interaction between distant dipoles, this Fourier transform is singular in the long wavelength limit, and it is precisely this singularity that mathematically gives rise to the halo, to the longitudinal transverse splitting that I tried to describe before. So in order to calculate this Fourier transform, because of this long-range contribution and this singularity, this Fourier transform would require, because of the singularity, a huge number of points to be calculated. A huge number of finely spaced points in Q space, or a huge number of distant points in real space. So this phi decays very slowly, so you need a lot of R space components to do the transform from R to K, and you need a lot of K points near the origin because of this singularity in order to do the transform from K to R, from Q to R. We don't want to calculate these dynamical matrices at too many points because these are expensive. Not as expensive as they would be with supercells, but still with the use of density functional perturbation theory, this is still an expensive process. So the trick that one uses is to exploit the knowledge that we have of the singularity. The singular part of D of Q has a well-defined mathematical form in terms of the effective charges. And the effective charges can be calculated rather easily as response functions at k equal to 0, at q equal to 0. So by calculating at q equal to 0 effective charges, we get all of the information that we need in order to separate out the singular part of the dynamical matrix from D of Q. So by extracting the singular part from the calculated D of Q, what remains is a smooth and well-behaved and non-singular contribution to the dynamical matrix that can be calculated and interpolated over few Q points only. Only after we calculate the D of Q over a rather coarse mesh, we then add back the singular part that is known analytically in terms of the effective charges. So this is an example of the first application of this technology to the calculation of lattice vibrations in elemental and polar semiconductors. As you see here, there are two features to notice. The first one is that the dots are experimental points, and the graphical dimension of the dots is of the order of the experimental incertitude. You see that the agreement between theory and experiment is of the order of the experimental accuracy. Very remarkable. This is the one kind of spectroscopy, so vibrational spectroscopy is the one kind of spectroscopy for which modern electronic structure methods give an accuracy comparable to the accuracy that can be achieved in the lab. Not yet so, unfortunately, for optical spectroscopies involving electron excitations. But as far as phonon excitations is concerned, this is the kind of accuracy that you may expect. Also important is this picture that is without experimental points. So aluminum arsenide is a very hygroscopic material, and it is very difficult to grow in samples that are large enough to be used in neutron diffraction experiments. So experimentally we know very little about the phonon dispersion in aluminum arsenide. But the confidence that the comparison between theory and experiment gives us for very similar compounds reassures us that we think that theory gives us access to those spectroscopic properties in that particular material that cannot be accessed in the lab. Few years after, Stefano Baroni generalized this technology of density functional perturbation theory to the case of metals. There is nothing particularly revolutionary to be added, but there are a few conceptual and practical issues to be addressed. Conceptual issues is to account for the response of the Fermi surface to the perturbation, and it is important conceptually and complicated in practice. this has been achieved almost 15 years ago, and the agreement is in this case as good as it was for insulating. So many applications have been attempted since the birth of the anti-functional perturbation theory 20 years ago already. These include the calculation of the electric, piezoelectric, and elastic properties of materials, phonons in crystals and alloys, and surfaces, interfaces, superlattices, and nanostructures, Raman and infrared activities. On Friday, you will learn how to calculate this, and calculation of anharmonic couplings using a third-order perturbation theory. So you can push perturbation theory one order further and get information on the phonon-phonon interaction that gives rise to the finite line width of phonon modes. Mode softening and structural transitions. We mentioned before that when a frequency becomes imaginary, this is a signal that a phase transition or structural transition may occur, and lattice dynamical calculations are a powerful tool to investigate such phase transitions. Electron-phonon interaction and superconductivity, thermal properties, isotopic effects, and many other properties have been studied. So this is a review paper that Andrea, Stefano, and Paolo Giannozzi wrote a few years ago that contains what was the state of the art at the date of publication. It contains virtually all the theory, and almost all of the applications existed up to that date. And again, these slides are available on the school wiki that by now is open to everybody. I don't remember the URL, but it's there. So ask me again later on, or ask Gabriele what the URL is. We have made our best to complete the program, including the title of the lectures, at least of those titles that are already available, and of presentations as soon as they are available. My own presentations are available also on my online website. Thank you for your attention. I will leave the stage to Andrea. I apologize for the usual delay, and I am available to talk to you, not now, at the end of the lecture.
Could you make this review paper available in your site so that I can?
I'm afraid that this is illegal. Because this would infringe copyright that is owned by the American Institute of Physics. So what I can do, I can give it to you. I think this is legal. But I cannot put it on my website.